We first walked onto site there in December 2014, and my last site visit onto site was in November of 2016. The principal contractor was Brookfield Multiplex, who are now Multiplex. Hopefully by the end of this case study, you'll have a better understanding of what we did there, and with a focus of the temporary works that was behind all of the magic that we did there. So this is, you can see the area there on the right hand side, it's in plan. So as I mentioned, we carried out the temporary works design services on behalf of the demolition contractor, who were John F. Hunt, and the whole scheme was worth 300 million pounds, and it was a grade 2 listed structure, which was the centre point tower. To realise the development, all the structures were to undergo significant alterations, which required some extensive temporary works, and this covered 3 main areas really, which are shown on the right hand side. So we've got centre point tower, which is the big tall tower that you can see from across London, and it's on the left hand side down here. You can see this is a more recent photo from Google Images, Google Earth, but that's the tower there. There's a link bridge that links the tower to Centre Point House, and this is all part of the same complex. The Centre Point House was on the right hand side in the blue box, and they are linked together with a link bridge. A road used to go underneath, and then there's an old pub, White Lion House, which is in the bottom corner there, which is highlighted in green. The principal temporary works included structural assessments on the global stability of the structure throughout the demolition. This work was carried out by us, and it was critical both at the top of the tower and also in Centre Point House. So at the top of the tower, significant demolition works on level 32 to the roof, so it's right at the top of the tower, and then the 6 floors of the residential housing above Centre Point House. That was the significant temporary works required there as well. Design of propping to facilitate the demolition of key structural elements until the installation of the proposed permanent works. We looked at the design of the false work and formwork for pouring the upper floors in the tower, which included the justification of that false work onto the existing structure. We looked at the design of the basement propping to facilitate the new 7-metre deep basement construction, which was in the White Lion pub, in the highlighted in green there. That included the approval in principle submission to the local council. Retaining wall analysis, there was a fair amount of work to do in the basement, so which included a lot of basement propping. And most designs were Cat 2 check risk category, and therefore we carried out those checks within the organisation. Our role also included some inspecting and signing off the more complex temporary work schemes. I was the lead designer, and I also acted as the temporary works supervisor on the job. And I visited once a week when things really started happening on site to support the site team and help them with the more technical engineering aspects of the works. There was a significant amount of the work that we did over the 2 years that we worked on that job, so I can't discuss all of it, but I'm going to do my best to take some of the key takeaways and discuss those. So the things that I'm going to talk about today is the temporary works associated with maintaining the global stability of the Centre Point House, the basement works in the White Lion pub, and finally we'll look at the temporary works at the top of the tower. The photo on the right there is one I took on my early morning walk onto site, getting off the tube, and you can see how exposed it is, and we had very little room around it, and it's very high profile, especially the works at the top of the tower. But firstly, onto the Centre Point House. This was a very groovy structure in terms of how it was constructed. There was sloped soffits, irregular column sections that changed as you go up, cantilever slabs, and also there was live residents in the flats above, which you can see highlighted there, and that was live throughout the works. And then also on top of that, the permanent work scope requires us to remove and gut most of the structure that was below those flats. So the stability assessment of the structure and the temporary works associated with that is what I'm going to talk about. So here you can see some of the structure in its real groovy glory. It was built in the 60s, late 60s, and yeah, there was lots of well, innovative designs done, as far as I can tell. They just wanted to throw everything at it that they had, I think. The columns being in an irregular shape posed quite a significant problem when trying to fit props around them, because every face was different, requiring a very flexible and changeable designs that we put in there. It wasn't a one size fits all. We had to put bespoke designs for pretty much each bay. On the left hand side, you can see some of the wire saw cutting, which we had a specialist team in for, considering that the cuts that were made were all different sorts of angles and locations and required a separate setup on each cut. Here we can see the extent of the demolition of the slabs, and you can start to understand that most of those slabs were on their way out. The problem this made for us is that the columns that were to remain supporting the structure above, which I may add included those live flats, would lose most of their lateral support. This has principally to do with the effective length of the column being tripled and sometimes a little bit more. A short, stocky column can take a greater axial force than a long, slender one. So if we remove the slabs either side of the columns or around the columns, which those slabs provided that lateral bracing, then irreversible damage would occur into those columns. Therefore, we had to brace them up whilst not clashing with the new floors that were to be constructed. So you can see from that little diagram at the bottom, there, a little schematic I've drawn up. So we were removing those floors which were providing bracing to that column. Once we removed those, the deflected shape is much increased, which means you get a larger eccentric moment into your column, which it wasn't designed for. So we had to review the stability of those columns and check them, which we did. And we found that in the strong axis, nothing was required. The columns were acceptable, but in the weak axis, they required that lateral support. So we designed some proprietary RMD frames between the columns in their weaker axis. The key issues with this design was that we had to get the propping to fit in between the existing structure to allow them to remove it, as well as making sure that we didn't clash with the permanent works. There was also a lot of other operations going on around site, so careful sequencing of installation and loading sequences were required. You can see that there's a hoist on the right hand side there. There's also a significant amount of propping and works in the basement around the lift pits, which we'll see on our next slide. We also have to think about preloading the system to ensure that there was no deflection once we removed those slabs. This was carried out through making sure that the jacks were very tight and monitoring the columns via spot checks with the total station to ensure that it wasn't moving, and also checking that markers on the screw of the jack didn't move during the shift. So that was checked. So this next photo, you can see that there's that ground floor slab, which was on the previous slide, had been removed, and then they'd also removed the basement slab as well to get the lift pit in. So not only were we taking out a number of floors, we were also exposing that column, which is the key column in the middle, which is the worst case, down to the pile head. There was some significant temporary works required elsewhere in Centre Point House, which unfortunately we haven't got time to go through today, but these were again principally to do with supporting the structure to ensure global stability whilst the demolition works and the permanent works were carried out. We produced a 3D model, which you can see at the top here. This was around one of this particular one is around one of the stair cores, which was basically all removed. And we supplied this model with 3D sequences, and also sent it in a 3D PDF viewer to the site team so that they could cut that that model up and just further understand the temporary works interface with the new and the old structure. it was essential to communicate that complex sequencing throughout the works to ensure effective implementation of that job. So now away from Centre Point House and down into the basement. Some of the basements were unlike the upper floors. That orange cross there, that shows where the link bridge is. So you had a road going over that at ground level, and then a link bridge over the top. But in the basement, they were all linked together. So the basement works were kind of grouped as one. The top photo on the right hand side just shows some of the guys core cutting for to install some of the piles that were the additional piles that were installed for the lift pits. And I'm looking there from just above ground level there, so it gives you an understanding of like how deep we went there. So the basement works I'm going to discuss here are those that were carried out in the old pub, the White Lion House. It was half existing structure and then half a new secant piled basement box. The Tottenham Court Road Crossrail project was just over the well, it was that they were our neighbouring project just over the road, and so we were able to use some of their leftover large CHS props that they used for some of their basement digs, which is why you can see that the photos there of those props that were spanning between the capping beams are pretty hench. They're very large, they're oversized really, but we used them, we recycled them from next door, which saved on transport costs and material costs, and also enabled us to be a bit more sustainable and recycle some material. The idea is the White Lion pub had a small basement, we were going much deeper on our new basement, so that's why we had to take out that existing basement slab and ground floor, which would provide the support to the that was existing support to the retaining walls, and put some props in to enable them to do a reduced level dig. Now, I mentioned the Crossrail project there. That was just next door. There was other tunnels to deal with. I think there was a central line and I think the northern line, I think. The secant piles therefore had to account for these tunnels. On the right, you can see, so that's on the left-hand side there, there's an exclusion zone of around those tunnels that was below this basement, which we took into account when we put together the approval in principle for that part of the job. On the right-hand side, you can see the propping of the existing basement, which we've used smaller CHS sections, which were fabricated for that particular task. We've utilised some Megashore RMD Megashore jacks and rocker heads to enable the props to be inclined. This enabled us to have some simple fabrication of the props themselves. They were just CHS props with end plates on, but it allowed us to have a lot more tolerance, which is very handy when you are in an existing basement, because the existing basements, it's just handy to have tolerance there, because a lot of the times it's not as clear cut as when you look at the drawings of what they should be really. So there's some other works in the basement, included some installation of some flying shores. And I've picked these couple of photos here just to explain about accidental impact. So all our propping was designed for accidental impact loads, because there was a lot of plant operating around there. There's like a skid steer in front there, and then down the bottom a block. And because of the demolition scope was quite close to where the props were, because the props had to be had to take over the load of what the existing structure that was being removed. That meant that they were working very close to one another, and that you can see that there's some damage to the prop there, which was because of the bucket was raised on the skid steer when it drove into it, which is not a clever idea, but as it's something there's a risk, then we design accordingly. It's good practice design for accidental impact loads, and that's for good reason. The things you've got to consider is how big is the plant, and that'll kind of give you an idea of how large of an impact load to design for, but also to think about robustness and designing for redundancy. fixings, connection points especially, to avoid catastrophic collapse of the temporary works and total removal of the system. Plastic failure of the steel of the prop, as shown there, with the plastic deformation of that flange, is acceptable in the short term, depending on how significant it is, but the total removal of the prop would have considerable consequences. You can look at robustness and try, but you've also got to think about efficiency, and you can't just have lots of props everywhere, because otherwise the demolition wouldn't be feasible. Here we've got a couple of props per, rather than having one big prop, we've got a couple of props per location. So if one was to go, that we've still got a prop there. So that they're the kind of things you can think about when looking at robustness of your temporary works propping. Elsewhere in the basement, there's an interesting scheme where we had to remove a ramp and provide propping around there. The ramp and its cheek walls had to be removed, so we had to prop around that. And you can see there's the block sat on the ramp and removing it, working down in a spiral. And we put the propping in there to mitigate that. And there you can see some of the new structure going in. Essentially, they didn't want the ramp anymore. They didn't need the ramp. They were using a fancy pants car lift to get the cars down instead of a ramp. So that allowed a lot more of the structure to be utilised for a space for other means. So that's the centre point house and centre point basements over the two areas. Now I'm going to discuss the most high profile part of the job, and high being the operative word there, because we're going to look at the high tower, centre point tower. The top of the tower, and removing almost all the floors in the top 3 levels, half of the roof, and a continuous strip spanning from one end to the other on level 32, which isn't actually shown on that schematic there. This required significant temporary works and also a 3D sequence. The site operations required meticulous control. Space was tight, plant was limited, access was via a hoist only. The sequence of the demolition was very complex because the global stability of that top of the tower relied on balancing the demolition on each side, as well as the progressive installation of temporary structures to provide the support. So what I mean by the progressive demolition is, if you can see my little pointer there, we couldn't start at one end of the demolition and work to the other end, because it would cause an imbalance of the structure. What we had to do is one gang would start at this end on that side, and one gang would start on this end on that side, and they would work together so that there wouldn't be too much of an imbalance between the structure that was removed, because we wanted to keep the centre of rigidity as close to the centre of the structure as possible to ensure that we kept the structure stable. And you can see the extent of the demolition there. We're removing pretty much all the structure other than the cores and some shear walls, and the facade was going to be kept because that was listed. So from the outside you couldn't see what was going on there. On the right hand side you can see that the permanent works proposal was to create some thinner floors and not so many floors, so that we could have some new fancy penthouse suites with a view like that. And that's what all that effort was for. A view over London from one of the few, there's a few double-storey penthouse suites right at the top of the tower. That's what all that effort was for. There's 3 key areas of the support systems to realise the demolition. Centre support in the top levels, which you can see on this drawing here. End support on the top levels around the lift cores, and also the level 32 central strip support. A key element of the top of the tower package was the global stability assessment, and then the design of the stability frames that ensued. These stability frames were comprised of, again, RMD, super slim soldiers and components that were located between shear walls, lifts and columns. And this is one of the drawings that we produced. So you can see there we've got a shear wall in the centre, and we're bracing it up, essentially allowing them to progressively remove the floors that are in between. And this is what it looked like in person. You can see that the roof is removed. A floor has been removed, which was so the roof has been removed up here. A floor has been removed here, and then they also need to remove this floor that's down here. This was a heavy construction because it was housed all the boilers and the boiler rooms that serviced the Centre Point Tower when it was in service. So it had large water tanks and things up here, which is why the structure was so heavy, and there was a lot of floors and steel beams in there. The idea was that they'd remove these floors and then just put a couple of floors in there, which would allow a lot more space now that the water is pressurized and gas is pressurized, and they don't need this large area for the service boilers and things. There's another photo there, and you can see that. So there's a facade retention support on the right hand side, and then there was really quite an open structure. This structure that we're stood on here, the slab that we're stood on here, that is also to be removed as well. So it's quite an open space when all that was removed. Here you can see they removed that slab that we were just stood on and replaced it with a formwork table. So this formwork table was sat on level 32, which is below. And you can also see that this column here, there was a change in section from, and the major axis was changed from kind of spanning this direction and to going this direction. That meant that there was a large concentration of stresses at this point, which we had to be really careful of. You can also see at the top there that there's a steel strip that was installed. That was to provide a tension capacity additional tension capacity to the shear wall, because it wanted to, this end wanted to drop off that way and this end wanted to drop off that way. So we had this steel strip that was installed at the top to keep it stable and keep it together. At either end, the lift cores, we provided some similar frames of RMD again, and they were installed between the cheek walls of the lifts to ensure that global stability. There's a photo of one there. We had jacks and timber packing at one end to allow for a bit of tolerance, so that the jacks would take in the compression, and this timber packing had 15mm Diri-Dag bars that were tied through and tied to the other side of the wall to keep it all tight, and then this member in the middle was on a turnbuckle, so you could turn that and stiffen the whole frame up before carrying out any of the demolition works. So how did we justify it? This is a drawing that we produced, which kind of shows what we did. We looked at each particular level and had a look at the destabilizing forces and checked that the stresses in the existing structure were acceptable. You can see on that right hand side of the drawing there just how empty that structure was. So this was level 32, and this central strip in the middle was going to be removed, and I'll show you that next. And then all this space in the middle was going to be open, other than the shear walls that you can see there, which are all designed to provide stability in one axis and not the other. This assessment all relied on sequence drawings, and it's a special sequence that was being carried out, like I mentioned earlier, the balance sequence. And we produced a 3D model of the structure, and that's the model that we used to provide that sequence, which is a part by part demolition sequence, so that there was no question as what part should be removed when. And this is a kind of an example drawing of what we did there. So it's a bit by bit. Stage 1, remove this part. Stage 2, remove this part. So it's very clear for the contractor on site of what to remove when. Now this is the level 32 removal works, and this is that central strip that we were removing. This central strip went pretty much from lift core to lift core, and so we had to install a series of temporary props to ensure that the structure didn't come apart in the centre, essentially. And this is that part there. During the process of the demolition of that central slab, we did come across some cracks. You can see the top there. Now these cracks were more than likely developed when during the demolition works, because there was a lot of vibration as they were using a block and a hammer attachment. And then they went after and neatened up the edges with localized cutting techniques. So this is a crack here. It's quite, you might be able to see it. They're a hairline, but because it was such a high-profile job and right up in the air, we wanted to make sure that no corners were cut. So we installed telltales and also monitored the structure was being monitored with a total station and marker points on the screws of the jacks, of all the jacks and the turnbuckles, which were checked at the beginning, during, at the end of every shift. Once we installed the telltales, there was no further cracking, or displacement was very minimal, but we wanted to make sure that it didn't go anywhere, essentially. This is the construction of the new, it was a post-tension strip that's being installed there. It was a post-tension because they wanted to really limit the depth of the central beam. And that was being installed right at the top there. That's why I've included that photo on the right hand side. So it was pumped all the way up to the top, and then that central part was cast, and then once that was cast and loaded up, then we could remove our temporary works. And this is the finished product. Ta-da! What an anticlimax. It's a dark grey structure, but it's really that was my last visit, so I'm sure now it looks like a really fancy penthouse suite, but the heavy plant structure that was there before is no longer there, and now we have two like a double-story penthouse suite with nice open plan space. So that's been the Centre Point development in a nutshell from a temporary works standpoint, really. We've covered the principal temporary works designs, which mainly included the global stability assessments and the propping that ensued to ensure that global stability was maintained during the works. Lessons learnt. I personally learned a great deal on this project. A key lesson being that providing illustrations and for complex structures and sequences is just immensely superior to any written instruction or spoken instructions. In this case, we produced a lot of 3D demolition sequences and showed the methodology of the demolition part by part. Another lesson I learned is coordination is key. A good relationship between the designer and the contractor is really helpful for effective project implementation of especially complex temporary works. I was on site every week when the temporary work started to get a bit interesting, and that really helped support the site team, as well as give me a better understanding of how the structure worked, so I could carry out more effective design. And finally, the other lesson is to be prepared for any unknowns, which is difficult because you don't know about an unknown, but it's just to keep an open mind, really. Asbestos that was uncovered within the tower, that they hadn't seen or reported on before, that costs the project a significant amount of time and money. And there are also discrepancies between archive drawings and the structure. It's important not to take the archive drawings as read. It's easy to go down the hole of it's been put on a drawing, and so and it's come with the structure, so it must be drawn like that, but you never know what was constructed last thing on a Friday, if you get that meaning. It's worth keeping an open mind when looking at the structure for details that may be different to what you've considered, and think about, well, what if it wasn't constructed like this? Thinking about lap lengths of bars, it's just worth keeping an open mind. think about things you haven't considered as well, latent defects, which is a fault in a structure that could not have been discovered by a reasonably thorough inspection. You can't find out everything about a structure without demolishing it, but there's a lot of, you can't, if you're demolishing, say, a slab that's providing a diaphragm support to a retaining wall, you can't do such thorough site investigation within that, as in intrusive investigation within that slab, because it's providing that support. So latent defects are always, and they carry a significant risk, which is difficult to eliminate. And just keeping your eye open around site for beauties like this little bad boy, which we found in the basement. This was like a homemade go-kart that we found on a site walk. That was inherited with the project. Flames, boilers. I mean, how can that not put a smile on your face? That's the centre point case study in a nutshell. I'm going to hand over to Angus. If you've got any questions, please feel free to put them in the Q&A bar, and we'll be going through that shortly. So I'll just hand over to Angus, and thank you for listening.
The reason